Alright, in this video we are going to be finding power series solutions to second order differential equations near ordinary points. To go ahead and start off, we're going to go ahead and define an ordinary point.
X equals x naught is an ordinary point if p of x and q of x are differentiable at x naught. Otherwise, it is a singular point.
We are always going to get our equation into the form y double prime plus p of x y prime plus q of x y equals 0. Find a series solution of y double prime minus x y equals 0. If you're looking for a singular point, come back in a later video, and that is going to be a lot longer of a solution. Anyways, we are going to always start with the assumptions that I'm writing out at the moment. We are going to assume that y is a sum of n from 0 to infinity, cn x to the n, and then we are going to derive this twice. So we have y prime and y double prime. This is because we need to be able to sub them back into the original equation with there being a second derivative. Notice that as I am making these assumptions and deriving, that I am just doing the power rule for the summation, but as I am deriving, I am increasing the indices by 1 each time. Now we are going to sub in our assumption into the original equation, hence why we derive twice, because it's a second order differential equation. So we are going to start with y double prime x to the n minus 2, and we are going to subtract by x multiplied by y. However, I'm not going to write this out twice, so I'm just going to write out the product, which stays the same, and we just increase the power by 1. This is equal to 0. Now, and these steps I'm doing should be your steps you do every time you solve for a series solution near an ordinary point. They shouldn't really change. You should always make this assumption up here, then sub it in, and then we're going to equate the powers of x. So we see we have x minus 2 and we have x plus 1. So we want to decrease this to x to the n and increase this to x to the n. However, as we increase the n's here, we also have to decrease, we have to oppose this in the indices. So this one, we're going to make the n's, we're going to plus 2 to the n, so plus 2 to the n, add 2 to the n's everywhere, and then the indices we're going to subtract 2 to the n. So it's going to end up being same summation, but the indices is going to start at 0, n plus 2 because we added 2, n plus 1 because we added 2, cn plus 2, and x to the n. Then subtracting, we're going to do the same thing for this summation. We're going to decrease the power of x by 1 to make it x to the n, minus the n here, and then we have to add 1 in the indices. So this is going to be n equals 1, cn minus 1, x to the n, and then again it's going to be equal to 0. Now that we've equated, so that was our first step right here. Second step is subbing in. Third step is equating the powers of x. Then the fourth step is going to be equating the indices. How do we do this? We run off terms to make. Luckily, this is only one term we run off because this indices start at 1, this one starts at 0, so we only have to run off one term from this summation to make the indices increase to 1. So when n equals 0, we get 2 times 1 times c2 x to the 0, so times 1, so it'll end up being 2c2 plus, and I'm going to put now both of these into one summation to make this nice and simple. Since both the indices now start at 1 since we ran off the first term. And I'm also going to pull out the x to the n. So it'll be n plus 2, n plus 1, c to the n plus 2, minus c to the n minus 1, close brackets, x to the n equals 0. If you look closely, I'll take my time here and just explain that this is from the first summation, minus, and that's from the second summation. Both these are multiplied by x to the n, so I pulled the x to the n out and rewrote the equal to 0. All right, now that we've ran off the terms, our almost final step is calculating the coefficients. So since this is a second order differential equation, we're going to make these two assumptions. C naught equals C naught and C1 equals C1 because there's two undetermined coefficients since it's a second order differential equation. So we have these, and also what we are going to do is solve these for 0. So first we're going to solve this, what's outside of the brackets, for 0. So 2c2 equals 0. We know that c2 equals 0. And then we're going to solve what's inside the brackets by setting what's inside the brackets equal to 0. And we're going to solve for the highest n. In this case, c to the n plus 2 is the highest. C to the n plus 2 is the highest, so we're going to solve for that to find our recurrence formula or our recurrence relation. So this ends up being c to the n plus 2 equals c to the n minus 1 over n plus 2, n plus 1. This is our recurrence relation. And this is when n equals 1, 2, 3, etc. You can see that I just took this term right here, solved for that, setting this whole thing equals 0. This goes the other side, and these go in the denominator. All right. Now we can start gathering our coefficients. We already solved for C2, so we can see that C2 equals 0. C3 ends up being C naught over 6. C4 equals C1 over 12. C5 equals 0. C6 equals C naught over 180. C7 equals C1 over 504. C8 equals 0, etc. Okay, so now that we have this, we can now gather C naught and C1 terms and form our first solution and our second solution. So we could say that y1 is equal to C naught 1 plus x to the third over 6 plus x to the 6 over 180 plus dot dot dot. And our second solution is gathering the C1 terms, x plus x to the 4th over 12 plus x to the 7th over 504 dot dot dot. And our general solution will just be y1 plus y2. And I'm not going to write that out because we have them right here. If you're kind of confused on where these numbers came from, what I did is I found all the C0 terms and I pulled out C0. So this I like to look at as our even series, and this is our odd series. So if we look, we have C0. If we pull out the C0 here, it becomes 1. And this, every coefficient is a different power of x, if you think about it that way. So c to the 4th is going to be x to the 4th right here. C to the 6th right here is going to be x to the 6th right there. So it just corresponds to the power of x. So when we gather up, we pull all the C0 terms. So we have C0 1, C0, and it's C3 equals C0 over 6. So it's x to the 3rd over 6. And then the last one in that one is C0 over 180. So it's pull out the C0. It is x to the 6 over 180. And then repeat the same thing for this one. All right. Going to solve one more example. And we are going to use the same steps. X or y double prime plus x squared y equals 0. And just like we did before, our assumption, we're going to let y equal the sum from 0 to infinity, cn x to the n, which means the derivative of that is n equals 1 to infinity, n, cn, n, x to the n minus 1, and the double derivative, indices goes up 1, power rule, n minus 1, c to the n, x to the n minus 2. All right, that's our assumption. And just like before, we are going to be subbing this back into the original equation up here. All right, so y double prime and n minus 1, c to the cn, x to the n minus 2, plus x squared times y. Here's y, and I'm going to multiply x in there, so it's just going to put a plus 2 here, but I'm not going to write it out twice, so I'm just going to write the product as before. N equals 0, x to the n plus 2. All right, this is equal to 0. Now, just like before, we have to equate the powers of x to x to the n. All right, so by doing that, we have the first one by going up 2 for all the n's. The n is going to go down 2, so it's going to start at 0. And now we got to add 2 to all the n's. N plus 2, n plus 1, c to the n plus 2, x to the n. Then we're going to add this sum But since we go down 2, the indices has to increase by 2. And all of the ends have to go down by 2, equal to 0. So now we have the equated powers of x. And just as before, our next step is going to be equating the indices. And how do we do that? We run off terms. This is the highest indices, so we're going to be running off 2 terms from here to make the indices match. So the first term, if you let n equal 0, is going to be 2c2, similar to before. And if you let n equal 1, it will be 6c3x. And then we are going to add the common sum. Now the indices for both are 2, so we can put them together. I'm going to pull out x to the n to make this neater. N plus 2, n plus 1, c to the n plus 2. I just pulled that from right here. And then we're going to add c to the n minus 2, which I pulled from right here. And it's multiplied by x to the n, and it is equal to 0. Now, we're going to do each factor of x, we're going to set equal to 0. So this is just a coefficient, doesn't have a factor of x. So we're going to set that equal to 0, which gives us c2 equals 0. This is the first factor of x, so we're going to set that equal to 0, which also gives us c3 equal to 0. And now that we're done with these coefficients, we are going to set this coefficient, what's inside the brackets, equal to 0, and find our recurrence relation, solving for the highest n, which is n plus 2. So c to the n plus 2 equals negative c to the n minus 2 over n plus 2, n plus 1, and that is our recurrence relation. All right, now that we have that, we can now make our table for the coefficients. Again, second order differential equation. We're going to make these two assumptions. C0 equals C0, C1 equals C1. And we are going to continue with our givens that we have solved for already. C2 equals 0 and C3 also equals 0. And then C4, using the recurrence relation, we're going to get negative C0 over 12. C5, using the recurrence relation, we are going to get negative C1 over 20. C6 is going to equal 0. C7 is also going to equal 0. C8 equals negative C4 over 56, which, looking up here, we can see that that's going to be equal to C0 over 672. And C9 is going to be equal to C1 over 1440 after doing the same algebra, etc. Thus, we can form our solutions. Y1 equals C0 times 1 minus x to the 4th over 12, hence right here, plus x to the 8 over 672 minus ... bang. And again, this came from right here. And our second solution can be C1 x minus x to the 5th over 20 plus x to the 9th over 1440 minus ... And our general solution is going to be y equals y1 plus y2, which you can write out, but I'm not going to. It's also good to realize that the coefficients or the n terms rely on the term 4 ahead of them. This one relies on this one relies on that, and hence y 6 and 2 are 0. Same thing on this side right here. And yeah, that is the end of finding power series solutions to second order differential equations near ordinary points.